Hello, welcome to the video of integral calculus, long divisions of polynomials. The intensity level is mild. By the end of this video, you should be able to compare the long division of polynomials with that of integers, use the long division to find the quotient and the remainder of the Euclidean division of two polynomials, use the long division to split a rational function into a polynomial and a proper rational function. Let's recall the Euclidean division of integers. So let A to be integer called the dividend and B to be a positive integer called the divisor. And then there will be two unique integers Q and R such that R is greater or equal to 0 less than B, and A can be written as the Q times B plus R. Then Q is called the quotient and R is called the remainder. So for instance, given the dividend to 20,212 and the divisor 113, how do you find the quotient and the remainder? The algorithm we will use is called the long division. By using that, we will separate the dividend to 20,212 and the divisor 113 by right parentheses and draw a vinculum above the dividend, where we would put above which we would put the quotient there. And the algorithm is that we will subtract from the dividend the multiples of the divisor 113, and then we put I will stack these the quotients, the coefficients on top of the dividend. So we would subtract from the dividend the 100 times of 113. We put 1, and we subtract 70 times of 113, and we put 7, and then we subtract 8 times of 113. We put 8 there. So in the end, we would subtract the 178 times of 113 from 20,212, and we would have the number 98 left. The 98 is less than 113, so it's the remainder. By the way, from that we know that the quotient, the fraction to 20,212 divided by 113 can be written as an integer 178 plus the quotient plus the rational plus the proper fraction 98 divided by 113. Now let's recall that we are using the decimal system, and the numbers can be written as the sum of the powers of 10. So 20,212 is written as the 2 times 10 to the 4th plus 2 times 10 squared plus 2 times 10 plus 2, or let's reallocate the powers so that becomes 10 to the 4th plus 8 times 10 cubed plus 18 times 10 squared plus the 38 times 10 plus 32. So this is actually a polynomial of x equal 10. On the right hand side, you can rewrite it as a parenthesis 10 squared plus 70 plus 8 parenthesis times 100 plus 10 plus 3 parenthesis plus the parenthesis of 9 times 10 plus 8. So this can be seen as a product of two polynomials plus another polynomial in terms of 10. So now we would let x equal to 10 and write the identities as an identity of polynomials, and we replace the numbers in the long division by the polynomials. We will see that the dividend is this long is x to the 4th plus 8x cubed plus 18x squared plus 38x plus 32. The divisor is x squared plus x plus 3. And we if we write now the and the quotient is x squared plus 7x plus 8. If we initiate the previous procedure, we get this. We are subtracting the multiples of the divisor from the dividend. We would get the remainder is 9x plus 8, and this calculation would be called the long division of polynomials. After that, we would yield Euclidean division of polynomials. This long degree 4 polynomials is written as x squared plus 7x plus 8 parentheses times x squared plus x plus 3 parentheses plus the remainder 9x plus 8. So in general, we have the theorem of Euclidean division of polynomials, and we have two polynomial ax and bx, when bx is non-zero. In one variable x, there would be unique polynomials qx and rx, such that, so here is we require degree of r is less than degree of b, and ax is equal to qx times bx plus rx. Now ax is the dividend, bx is the divisor, qx is the quotient, and rx is the remainder. Okay. And when we use the Euclidean division, we can rewrite given a rational function with perhaps a very large numerator. We can rewrite it as the sum of a polynomial plus a proper rational function, so that the numerator degree is lower than the degree of the denominator. So this is our application of this Euclidean division. The algorithm would be the same as similar to the long division of integers. Now, the first example, find the quotient of and the remainder of the division of 2x minus 3 by x squared plus 1. So if we look at the dividend, its dividend has degree 1, and the divisor, or the denominator, x squared plus 1, has degree 2. So this guy, so the dividends already have lower division, lower degree. So the remainder is there's nothing to divide from that dividend. So the quotient is 0, and the remainder is the 2x minus 3 itself. The Euclidean division is written as 2x minus 3 equal to 0 times x squared plus 1 parentheses plus the remainder 2x minus 3. And you see the rational function would be 2x minus 3 divided by x squared plus 1. So it's already a proper rational function, so there's no polynomial part. In the second example, the dividend is 2x cubed minus x minus 1, and the divisor is x minus 1. So we would really, since the dividend has a higher degree, we should really use the long division. So we place this divisor and dividend in the right position, but here it's like when we do the integers, we would put 0 even if there is no multiple of 10 power, like 1, 0, 2, 3. For polynomials, we would also add this missing terms like plus 0x squared over here. You can choose not to write it here, but you should at least leave the space for the square term. And first we compare the highest term of the dividend to x cubed, and with the highest term of the divisor is x, and we divide them with the quotient 2x squared will be the first term of the quotient we put above the vinculum 2x squared, and note that how the 2x squared is aligned with the x squared term. Then we would multiply 2x squared by the divisor. We get 2x cubed minus 2x squared, and we put it below. Then we draw a horizontal line, and we would compare those two lines above the horizontal lines. So and subtract them. We get 2x squared minus 2x squared, and there's nothing to subtract. But for the next step, we need to bring down the next term minus x below the from the dividend below the horizontal line. And then again, so here 2x squared divided by x is 2x, and 2x multiplied by x minus 1 is 2x squared minus 2x. And we draw a horizontal line again, and we're going to subtract these two. We get x, but there's a minus 1 term we put down from the dividend, and then x minus x divided by x. So there's only one multiple of x minus 1 from the x minus 1, and you can see that there's exactly x minus 1. So there's x minus 1 is itself divisible by the denominator, and so the remainder is 0, and we stop because we see the remainder is 0. It has, so we have a divisor is a 1, it's degree 1, but we already have a constant left, so we can stop here. And now we can read the quotient from the first line, 2x squared plus 2x plus 1, and the remainder 0 from the last line. The Euclidean division is quite simple form with the 2x cubed minus x minus 1 is multiple of the two polynomials without a remainder, and the rational function would become 2x squared plus 2x plus 1 is a polynomial itself. There's no proper rational term part in this case. Now the third example, we have the numerator x squared plus 1 parentheses squared, and the denominator x plus 1 parentheses squared. So in order to do the long division, we need to first expand the dividend and divisor so that there's no parentheses, and we put them in the right places. X to the fourth plus 0x cubed plus 2x squared plus 0x plus 1, and x squared plus 2x plus 1. So first step, we compare x to the fourth divided by x squared, get x squared. So this will be the first term, and here you should note how this is lined with the x squared term of the dividend. So we subtract. Now we subtract so the first term would always be cancelled out, but the second term minus 2x cubed, and third term is 2x squared minus x squared, get x squared. And we need to drag out the non-existing 0x from the dividend, and we keep going, get minus 2x. So we multiply, and the difference is 5x squared plus 2x, and we drag plus 1. So then we plus 5, we take a copy of 5 times of the divisor here. The rest is minus 8x minus 4, and now the divisor, there's no copy of the divisor from it, because now the remainder is already degree 1, but the divisor has degree 2. So we should stop here. The quotient, now we read the quotient, x squared minus 2x plus 5 from the first line. The Euclidean division yields that the numerator is equal to x parentheses x squared minus 2x plus 5 times the denominator plus minus 8x minus 4, and the rational function, the square divided by square, is a polynomial x squared minus 2x plus 5 and plus minus 8x minus 4 parentheses divided by the square x plus 1 of x plus 1. So this is how we calculate for this division. There's another approach. If you don't want to expand this denominator, you can try to change the variables, like y equal to x plus 1, and the denominator becomes y squared. Now the dividend you need to expand, and you can either expand first and then plug in, or you can like what I'm doing here. You first plug in and try to expand. Plug in x equal to y minus 1, and you get parentheses at y squared minus 2y plus 2 parentheses squared. You need to use the square of the sum formula. So the square of the three terms, y to the fourth plus 4y squared plus 4, and minus times the 2 times the two times of the cross terms, minus 4y cubed plus 4y squared minus 8y, and I'll get this. So the rational function would become a very simple denominator x y squared, and a numerator is a long numerator. And here the since the denominator is a monomial, you can easily find the polynomial part, y squared minus 4y plus 8, and the rest is lower degree part, minus 8y plus 4 divided by y squared. And if you change the variables back, you get in terms of x, it's the same as the first approach. So here we have avoided the long division, but the cost is at the cost of changing the variables twice. So depending on your flavor, since if you want to if you want to integrate this rational function, the advantage of this method is that you do not have to change the variables back after you get the second to last step, because it's even easier to integrate in terms of y. Okay, so you get like minus 8 divided by y plus 4 over y squared, and each term you can integrate term by term very easily, and then plug in y equal to x plus 1 after you integrate. So here we have introduced the method and shown some examples. The reflection: why do we need to compare the degrees of the dividend and divisor before we applying the long division? What should we do if the divisor is a monomial? In case the dividend and divisor has common divisors, could we simplify the process of the long division? And for integers, if we keep the division process, we do not stop, but we keep doing, and even beyond the decimal point, we will get the quotient have the decimal part. Either it will be a terminating decimal or repeating decimal. So what would happen if we continue the long division process for polynomials beyond the constant term? Okay, thank you for watching.